17.2 Non-homogeneous linear equations. In this section, we learn how to solve second-order non-homogeneous linear differential equations with constant coefficients, that is, equations of the form equation 1 a times y double prime plus b y prime plus cy equals big G of x, where a, b, and c are constants and big G is a continuous function. The related homogeneous equation, equation 2, a to the power, equation 2a y double prime plus b y prime plus cy equals 0 is called the complementary equation and plays an important role in the solution of the original non-homogeneous equation 1. Equation 3 is a theorem. The general solution of the non-homogeneous differential equation 1 can be written as y of x equals y sub p of x plus y sub c of x, where y sub p is a particular solution of equation 1 and y sub c is the general solution of the complementary equation 2. Proof. We verify that if y is any solution of equation 1, then y minus y sub p is a solution of the complementary equation 2. Indeed, a open y minus y sub p close double prime plus b open y minus y sub p close prime plus c open y minus y sub p close equals a y double prime minus a y sub p double prime plus b y prime minus b y prime sub p plus cy minus cy sub p equals open a y double prime plus b y prime plus c y close minus open a y prime sub p plus b y prime sub p plus c y sub p close equals big G of x minus big G of x equals 0. This shows that every solution is of the form y of x equals y sub p of x plus y sub c of x. It is easy to check that every function of this form is a solution. We know from section 17.1 how to solve the complementary equation. Recall that the solution is y sub c equals c sub 1 y sub 1 plus c sub 2 y sub 2, where y sub 1 and y sub 2 are linearly independent solutions of equation 2. Therefore, theorem 3 says that we know the general solution of the non-homogeneous equation as soon as we know a particular solution y sub p. There are two methods for finding a particular solution. The method of undetermined coefficients is straightforward, but works only for a restricted class of functions big G. The method of variation of parameters works for every function big G, but is usually more difficult to apply in practice. The method of undetermined coefficients. We first illustrate the method of undetermined coefficients for the equation a y double prime plus b y prime plus cy equals big G of x, where big G of x is a polynomial. It is reasonable to guess that there is a particular solution y sub p that is a polynomial of the same degree as big G, because if y is a polynomial, then a y double prime plus b y prime plus cy is also a polynomial. We therefore substitute y sub p of x equals a polynomial of the same degree as big G into the differential equation and determine the coefficients. Example 1. Solve the equation y double prime plus y prime minus 2y equals x squared. Solution. The auxiliary equation of y double prime plus y prime minus 2y equals 0 is r squared plus r minus 2 equals open r minus 1 close open r plus 2 close equals 0, with roots r equals 1 and negative 2. So the solution of the complementary equation is y sub c equals c sub 1 times e to the power x plus c sub 2 times e to the power negative 2x. Since big G of x equals x squared is a polynomial of degree 2, we seek a particular solution of the form y sub p of x equals big A x squared plus big B x plus c. Then y prime sub p equals 2 big A x plus b plus big B, and y double prime sub p equals 2 big A. So substituting into the given differential equation, we have open 2 big A close plus open 2 big A x plus big B close minus 2 open big A x squared plus big B x plus big C close equals x squared, or negative 2 big A x squared plus open 2 big A minus 2 big B close x plus open 2 big A plus big B minus 2 big C close equals x squared. Polynomials are equal when their coefficients are equal. Thus, negative 2 big A equals 1, 2 big A minus 2 big B equals 0, 2 big A minus, 2 big A plus big B minus 2 big C equals 0. The solution of the system of equations is big A equals negative 1 half, big B equals negative 1 half, and big C equals negative 3 over 4. A particular solution is therefore y sub p of x equals negative 1 half x squared minus 1 half x minus 3 over 4. And by theorem 3, the general solution is y equals y sub c plus y sub p equals c sub 1 times e to the power x plus c sub 2 times e to the power negative 2x minus 1 half x squared plus 1 half x minus 3 quarters. If big G of x, the right side of equation 1, is of the form big C times e to the power kx, where big C and k are constants, then we take as a trial solution A function of the same form lies to p of x equals big A times e to the power kx, because the derivatives of e to the power kx are constant multiples of e to the power kx. Sidebar. Figure 1 shows 4 solutions of the differential equation. In example 1, in terms of the particular solution, y is to p and the functions f of x equals e to the power x and g of x equals e to the power negative 2x. See figure 1. There's graphs y sub p and y sub p plus 2f and y sub p plus 3g and y sub p plus 2f plus 3g.